Hello, IP Physics students, Dr. Brenzi here, and this is problem number 1 from lesson T3.R1. That's our trimester 3 review. And in this lesson, we covered linearization, the idea of using linearizing a graph and extracting information from that. So let's go through problem number 1. It says here, a student's given the set of orbital data for some moons of Saturn in the table below, and is asked to use the data to determine ultimately the mass of Saturn. And we can assume that the orbits of these moons are circular, which sounds like a key piece of information. We probably want to start thinking about circular motion when we work through this problem. As you can probably see, the data are handwritten in. That's because I don't want to use the actual numbers that are given to you on the problem set so that you can actually determine this yourselves. So let's go ahead and get started with part A. It says, write an algebraic expression for the gravitational force between Saturn and one of its moons. Okay, so we have two celestial bodies. The gravitational force between those is given by Newton's law of universal gravitation. And that law states that the gravitational force is equal to negative g times m, the mass of Saturn, times little m, that's the mass of the moon, over r squared, where r is the distance between them, which would be the orbital radius of the moon. Okay, so that is what we needed to write for part A. Really simple. Usually AP style questions on free response usually begin with like really simple matter of the fact type questions. They want you to kind of like get into it and get you some good points, get you some free points actually. So there we go. It does get a little bit harder here, especially in part B. Now let's. It says here, use your expression from part A and the assumption of circular orbits to derive an equation for the period t of a moon as a function of its orbital radius r. So we're being asked to express a relationship between t and orbital radius r. So I'm being ultimately asked for an equation that looks like this. T is some sort of function of r. I don't know what that function is. That's what I have to find out. It does tell me, it gives me a hint as to the concepts that I should use. First of all, it tells me I should use the expression from part A. So I did that. Or we're going to do that, which is this equation right up here, of course. There we go. And the assumption of circular orbits. So I better be thinking about properties of circular motion when I'm thinking about figuring out what this relationship has to be. Okay, now let's see what we can come up with. I'm going to go ahead and create a new slide just for this step. So let's go ahead and draw Saturn and one of its orbits. Or one of its moons, excuse me, in orbit around Saturn. So here's Saturn. I even drew a little bit of a ring there. And then this is the moon up here. Okay, so the force that's keeping this moon in a circular orbit is gravity. So gravity is always pulling that moon toward the center. And if that force is always pointing toward the center, then, well, that has to be the centripetal force. So if I write F net equals ma, then I know that the F net, the net amount of force, is that gravitational force. And since this is always pointing toward the center, this force has to be providing the centripetal acceleration. So A is going to be centripetal acceleration. All right, well, I can replace Fg with the expression I had in part A. So let's do that. And then I can replace a sub c, centripetal acceleration, with v squared over r. Well, that doesn't quite give me anything that is involving the period of the motion of this moon. It doesn't give me the period, but it does give me velocity. So what I can do next is say, okay, is there a relationship that I can come up with between velocity and period? And, well, it makes sense that if I'm traveling at a velocity v, and it takes me this amount of time, some time t, then I'll get all the way around the circle. So that velocity, oops, let me talk about that in a minute. It looks like I just simplified some things there. But what I can say is that the velocity of this moon has to be the entire circumference of the orbit divided by the period of the orbit. So v equals 2 pi r over t. Okay, let me back up. In case you didn't see what I did here between this step and this step, it looks like I just a little bit of simplifying. It looks like the m's divide out, the negatives divide out, and it looks like one of these r's will multiply out with that r over there, and so that's how I got this expression right here. And then what I'm going to do is replace v squared with this guy right here, 2 pi r over t. And so now I have some sort of relationship that involves both the radius of this orbit and the period of that orbit. Now I just have to solve this thing to get t by itself. Okay, now I'm going to do this in a slightly roundabout way, but I'll show you why I'm going to do it this way. You probably will take a more direct route since you're more interested in answering the question, but I wanted to show you something first. All right, so what I'm going to do is I'm going to multiply both sides by r. You might have thought about taking the square root of both sides first, and that would have been perfectly legitimate, but I want to show you something, like I said. So now we have g times the mass of Saturn equals 4 pi squared r cubed over t squared. And then if I multiply both sides by t squared, I get this relationship. And then if I divide both sides by g times the mass of Saturn, I get this relationship. Now, I did this because you may recognize t squared is equal to some constant times r cubed. And that happens to be Kepler's third law, which states that the period squared is proportional to the radius cubed of any orbit or of any satellite that's orbiting around a planet or star. So there you go. It's Kepler's third law. T squared is proportional to r cubed. All right. Now let's go ahead and take the square root of both sides to finally get t. And you'll notice you come up with something like this. All right, now what I would like to do is I'm going to actually separate this term under the radical into a part that's constant and a part that depends on r. So let's do a little separating right there. And then I'm going to express this as r to a power. And of course that power would have to be r to the 3/2. So now I have t as a function of r. Oops. Let me back that up. Sorry about that. So now I have t as a function of r, and that's what it was asking me for in part B. Okay, for part C, it says which quantities should be graphed to yield a straight line whose slope could be used to determine Saturn's mass. Wow, that sounds like a lot. But this is the process of linearization here. This is the whole big conceptual part of why linearization is so useful. So, let's first of all imagine that we're going to just plot t versus r. Actually, let me even back up more than that. Let's imagine that we have a function y, and that's equal to some constant times x to some power n. And if I were to plot y versus x, you know that I would definitely not get a line unless n equals 1. So if I were to plot this, I might get some sort of curve. Okay, now, it would be a lot more helpful to get a line, because with lines you can actually calculate slopes, and you can do that very accurately. So what I would like to do with this function is make it something that would be linear when plotted on a graph. And the way that I do that is I say, okay, let's create a variable w, which is equal to x to the n power. So I can replace x to the n with w, and now I have y equals c times w, and we know that if we plot y versus w, we are going to get a straight line, just like that. In addition, the slope of that line is going to equal this constant c. So we can actually use linearization to determine this constant c when we have a relationship between y and x to some power. And the idea of letting w equal x to some power is the idea of linearization. We are changing this graph into a line. Now, plotting y versus w is just like plotting y versus x to the n power. So if I, instead of just using x down here, I use x to the n and I calculate that and plot that versus y, then I'm going to get that same straight line that I had when I had y versus w. Okay, so let's see how that applies to this particular problem. Okay, so we came up with a relationship that says t is equal to some constant times r to the 3/2 power. So when I plot that, when I plot t versus r, I am going to get some sort of curve. I'm not going to get a straight line. I would love to get a straight line, that way I can calculate the slope and use that slope to figure out what this number has to be. In order to do that, I have to follow this process of linearization. So I'm going to let w equal r to the 3/2. Now what I have is I now have t is equal to that same constant times w. And now if I plot t versus w, I am going to get a straight line. Now we said that w is r to the 3/2, so if I plot t versus r to the 3/2, I will get a straight line. So plotting t versus r to the 3/2 will yield a straight line, and the slope of that line will give me this constant right here. Okay, now that we've figured out what we need to plot, let's go on to part D. Oh yeah, plot t versus r to 3/2. I told you that, but I didn't write it down. There we go. Now let's go on to part D. Okay, so in part D, we're turning our attention back to the top of the table, back to the table, which is at the top. And they give us 2 extra columns in the problem because what they want us to do is they want us to calculate those 2 values that we came up with. We came up with t in seconds, and we came up with, oops, I gave you a number there. Let me talk about that number. Since this is t, and that's t, I just have the simple task of rewriting these numbers over here, so that shouldn't be terribly hard. I'm going to skip the rest of those because I want this video to be fairly short. And what we want to plot versus that, or with that, is r to the 3/2. So this is r to the 3/2 power. And when you take a distance to the 3/2 power, you have units of meters to the 3/2 power. That's an awkward unit, but that's the unit we need to use when we're talking about length to the 3/2 power. All right, so what I need to do is I need to take this number and raise it to the 3/2 power on my calculator. And when I do this first one, I get 5.7 times 10 to the 13. I'm sorry you can't see that number terribly well. Looks like it's pretty small. But you could also do that for the remaining rows as well. This number to the 3/2 power will go in here, and so on and so forth. Okay, so you will fill in these two columns of data with t and with r to the 3/2. Okay, so that's part D. I'm not going to finish the rest of the table because I got to give you some work to do. When we do that, we need to now graph t versus r to the 3/2, just like we said we would do in part C. So let's plot the graph on these axes below. And this is super, super important for AP exam. They want you to carefully label each axis and use appropriate numbers to indicate the scale of the graph. So they are very particular about both of those things. So I'm going to go through those. Don't skip over this part. Okay? A sketch will get you very few points on this part, and they're easy points to pick up, so don't skimp on this, please. All right, let's get going with this. All right, so we said we're going to plot t in seconds along the y-axis, and we're going to plot r to the 3/2 along the x-axis, and don't forget to put your units in parentheses. I left a little bit of room because I am going to take a little bit of an allowable shortcut that will make my graph much neater in a moment. So what I'm going to do next is I want to create an appropriate scale. So if I go back to my table, I would like my lowest value of t to be somewhere down here on my graph, somewhere in this region, and my highest value of t to be somewhere in this region of the graph. Okay. So what I would do is I would say, okay, maybe this one, well, first I got to label my zeros. I forgot about that. But the second thing I need to do, I noticed that the first value is somewhere around 3.7 times 10 to the 5th seconds. Now notice I'm not going 2 times 10 to the 5th, 4 times 10 to the 5th, 6 times 10 to the 5th. I'm just doing 2, 4, 6, 8, 10, and then I can take a shortcut and just write 10 to the 5th power right there, 10 to the 5th. Oh, for some reason I wrote 10 to the 8th. I'm not sure why I did that. Hold on here. Maybe it was 3 times 10 to the 8th. Okay, maybe I'm misremembering that. Sorry about that. Okay. I'm going to do the same thing along the x-axis here. But I notice that along the x-axis I am beginning at a number. Let's go back actually. I'm beginning at a number that is about 5.7 times 10 to the 13. Okay. Now this causes a bit of a problem for me. Whoa. Oops. I gave you the I skipped to the end. Oh no. All right, let's go back to where we were. All right, so you got a sneak preview of what it's going to look like in the end. Oh, that does say 10 to the 8th seconds. I'm sorry. I'm having a hard time reading my own handwriting. Now, instead of going 2, 4, 6, 8, 10, I decided I want to actually start this somewhere near the number 6 times 10 to the 13. Because 5.7 times 10 to the 13 will be somewhere in this region right here. Okay. All right. Now, if I decide that I want to start at a number 6, notice that this scale is not even. I jump from 0 all the way up to 6 and then go 7, 8, 9, 10. Now, if I did this, I am going to lose points. Unless I indicate to somebody that I am breaking the scale at the beginning. If you want to break the scale at the beginning, and I would recommend this, especially if you want to get a cover the entire graph, and that's actually what they want you to do on the AP exam. So if we have to create a wacky scale like this where we're starting at 6 and going up to 10, then I have to put a break symbol right here. And that break symbol looks like this. It's like a sideways Z, or it's actually, if you put it on this axis, it says Z. It almost looks like you're squishing a line is what it's supposed to look like. That's what's called a scale break. So we need to put a scale break in here if we are creating an uneven jump here from 0 to 6 at the very beginning. Okay. All right, so now that I have a good scale on both of my axes, I can go ahead and plot my numbers. So I'm going to go ahead and plot my first data point right here. That's the actual data point that I calculated. I didn't calculate the rest, so I'm going to make up 3 more numbers or 3 more points on this graph. So let's say that those 3 points look something like this. I don't know if that's actually correct, but that's not important for showing you the process of linearization. The last thing I have to do is come up with a best fit line. What I do not want to do is I don't want to connect the points of the line. I want to create a straight line, and I want to create a line that represents kind of like the best fit. But it takes into consideration that there might be some errors in these numbers. What might be a good representation of a best fit might be this line right here. Now notice that this line doesn't go through any of the points, and that's perfectly okay. What you should have, you should have roughly half of the points above, half of the points below. It doesn't have to be exactly half, but it wouldn't be nice to be half. What you're ultimately trying to do is try to find a line that has like the least amount of space from each of these points. Okay, that's kind of how a best fit line works. All right, now what I want to do is I'm done with part E, but part F says, now use that graph to calculate the value for the mass of Saturn. We came up with a best fit line, so this would be my best fit line that I just drew. And there's some connection between this line and this formula. If you don't remember what that connection is, you might want to go back to where I was talking about part D, or was it, no, it was part C, excuse me, when I was trying to figure out what I need to plot on the Y and the X axes. And I'll put a little thing down here to tell you where to go back in time if you need to rewind this and look back at that again. Now, if that's tripping you out, here might be a bigger clue. Remember that we called this r to the 3 halves w. So you could almost think of this as like t is equal to this times w. And how would this line be related to this formula right here, specifically this constant right here? So that's the big connection that we have to finish up with. And once we finish up with that big connection, then we can use that to calculate the mass of Saturn, which is inside this constant. Okay, so I've left you with still some work to do. I don't want to give everything away because I want you to enjoy the process of figuring out what the mass of Saturn is without having to look it up on Google or look it up in my table. Okay, there's a long video, but hey, linearization is a long process, and they would give you 15 minutes to do this entire problem, and it took me 10 extra minutes of explaining, so there you go. All right, team, I hope to see you soon. I hope you enjoy your day tomorrow, wherever you might be. Stay safe, and I'll see you the next time I see you. Bye.